Hello. Hello, good morning. Good morning, Clinio. How are you?
Hello, Akira.
Audible? Is it audible to you?
Yeah, can you hear me? Yes.
Hello.
Hello.
This sound is not audible. Hello.
Hello.
No, no. This sound is not audible. Hello. Could you talk again, please?
Yes. Yes. Hello.
It's very feeble. The sound is. Hello.
Hello.
Can you hear me?
Yes. Yes. I can hear you.
Okay. Could you talk something? The sound
Yeah,
is
let me
not
just.
so clear here.
Yes.
The
Hello. Hello. Hello.
volume is.
Can you hear me? Hello.
Maximum.
Yeah, can you hear me? Hello.
Yeah.
Okay. Good.
Yeah. Now it's audible. So, hello. Okay. Good afternoon, everyone. So we are resuming the second half of the session 2, the second day of the workshop. So for the afternoon session, we have two presentations. One is now for therapy of autistic children by Laura Santos and NVIDIA Isaac Lab, Manuel Serra and Nuno Duarte. So I welcome Laura Santos for the first talk.
So Laura, let me just. We'll try to send her a message because I don't see her here. She's about to enter, so just a couple of seconds. So she's
Okay, sure,
coming
sure.
in.
Yeah.
So she had to reboot her PC, but probably a couple of minutes and then she will be in.
Okay, fine, fine.
Yeah. In the meantime, I can
Yeah,
give
but just one query regarding the time constraint only. Since it is Friday,
yeah,
Friday evening here, the students may want to leave a bit early. There are some parallel events are also happening currently called Arush, which is
yeah,
the university level festival. So now we are planning if we could take the break by, there it is time, 9 o'clock, right?
yeah. Right now,
So
yes.
if it will be better if we can stop by 9:50,
9:50. Yeah.
9 to 9:50, then 10 minutes break. And the next session will be starting by 10 o'clock.
Uh-huh.
Yeah, 10 to 11. Will that work?
Yeah, I think that's fine. Yes, yes.
Okay, okay, fine. Yeah.
So before I can give a quick like introduction about Laura. So she
Yeah, sure, sure. Yeah.
yeah, so she finished her PhD like a couple of months ago, and her PhD was about doing therapy for autistic children. So and so she went through. It was partially in Portugal and in Italy. So she went to places in Portugal where they have therapy sessions for autistic children, and also she went in Italy to in Milan to also to do the same kind of sessions. So and on the sessions she used the NAO robot. The NAO was doing some gestures, and she was using also an external camera, that the camera was actually looking at the persons, and it was detecting the positions of all the joints. That was more or less the basic setup. So she has been playing around with the NAO for a long time with multiple sessions. So it was and yeah, that's all I can tell. So she's about to enter soon.
Yeah. Yeah, I think she's connecting now.
Hi, I'm sorry. I had
Yeah,
some troubles.
yeah, yeah, it's
I know
audible.
that.
Welcome, Laura.
Thank you.
You may start the
Okay.
session. Yeah. So the plan
Okay.
is till 9 to 9:50 is the session planned. 50
Okay.
minutes.
Perfect.
Okay. Yeah, thank you.
Okay.
Please go
Let
ahead.
me just put also clock. Stopwatch was clock. No. Okay. So you can see now my screen, right? Yes.
Yes, yes,
Okay.
we
Okay. So I will go. So hello, everyone that is there. I will start this session. My name is Laura Santos. I'm a PhD. I have just done my PhD in VisLab. Today, I'm going to talk a bit about my work and the work that we have developed in VisLab, and we will have like a small demo if it works, if my computer doesn't decide to crash, about this topic that is robotics. The overall topic is robotics for the therapy of autistic children, and we are going to especially focus on the now robot and the use of choreograph. Choreography is one of the things that I will use in this for this demo. So here the outline of the presentation. So I will start with the motivation for this work, what we have reviewed in the literature, some of the goals. Then we will go through the clinical protocol. Sorry, there are a lot of things appearing. And then I will focus on the implementation part, how we have done so far, and what could be the connections, and then depending on the time, I have like the measurement part, that is an important part also of the work developed and some of the studies, and finally the conclusions. So starting from the motivation for this work, just to, I don't know how much you know about autism, just to give a general overview. So autism spectrum disorder is a neurodevelopment disorder whose prevalence has been rising overall in the world. Here I have statistics in Portugal and Italy, because my PhD was developed in these two countries, so you will see things of Italy and things of Portugal in this presentation. And autism spectrum disorder is characterized by social communication and social interaction deficits, and also by the presence of repetitive, restrictive, and repetitive behaviors. It is a multifactorial disorder. That means we don't know exactly what causes it. So there has been a lot of work in terms of finding some kinds of biomarkers, something that identifies the disorder, that we could understand sooner the disorder. So some have developed tools with magnetic resonance, with electroencephalograms, and others have developed some more tools in the part of non-verbal communication, specifically in some of the deficits of these children that are regarded with attention and with the gesture. So these children have difficulties producing gestures. And that leads to a huge heterogeneity that characterizes this disorder. So there is no one fits all solution. There are a lot of therapies, a lot of alternative therapies, and that is there that we introduced ourselves, that is in the robotic therapy. So a therapy in which we have a robot, the child, and the therapist. Why these therapies are used? Basically because robots have simplified expressions compared to humans. They are predictable, and what we have seen so far from the literature is that these children have empathic behaviors towards robots, like neurotypical, so the ones that are typical children have normally towards adults. And that has led us to a literature of the review. I will pass much of it, but basically we have seen the review, a lot of articles, like 100 articles, to understand the state of the art in this topic, in robotics for autism. And what we understood was that most of these sessions were very small sessions. It was like pilot studies with 5 sessions, with few number of participants, and with an interaction just between the robot and the child. So not a real triadic interaction. That is something that we have more in the daily life. In the daily life, the robot is not there, the people are there. So we just had like this interaction between the robots and the child. And in terms of controller, let's say, what we have in most of the cases, it's a kind of Wizards of Oz type of control. That means that the robots are basically controlled from another room. And this is really not feasible for long-term studies. If we have like several sessions, if the therapy has to do and long for several of sessions, we don't have this is not feasible. And moreover, most of the measures that we took out of these therapies were manual measures, and instead of more automatic, could permit the comparison between the studies. So all of these leads to a huge gap between the research that has already been done. So this field has already 20 years, and what arrives to the clinical practice, to the clinical life. And that are our goals, that is to develop clinical inspired protocols, to have more automatic measures, and to design experimental studies for effectiveness evidence. So through my presentation, I will pass from these several topics, and it's in the clinical inspired that I will pose my part of the workshop. So regarding the clinical protocol, so in all this work, we always pass for a first step, that is understanding what the clinics want, like what is important for them and what should be done, what they need. So the first step for us was to talk with Fondazione Don Carlo Gnocchi, that is a foundation in Italy, specialized in the rehabilitation of children, and we try to understand what they wanted. So what they told us is that for them it was important to have non-intrusive sensing, so sensors that the children didn't have to use, not to touch, because these children have a lot of sensibilities in terms of the sensor part, so they don't like to wear things. It should be an interactive protocol that involves both the therapist and the child, and that has like some kind of functional movements. So we decided to use as main sensor a depth camera that you have probably seen before, that is the Kinect V2 camera, and associated with a commercial robot that was NAO robot. And we have developed these triadic interactions between the robot, the child, and the therapist, and developed different kinds of algorithms regarding this scenario. So the way that we have implemented this was basically what the therapist told us. So it's not that we invent this, is what they thought it was better. And it was interesting for us to develop a lot of algorithms after it. So we had the NAO that shows the exercise, the adult that does the exercise while the NAO is mirroring him, and then is the turn of the child. And with this, we had two different reactions from the patient, one that was very suspicious, and in the end, it was completely engaged, and another that was kind of discomfort with the increase of movement complexity. So when we went to more complex movements like dragging or picking that involve the two arms, it was more difficult. And that's why we decided to create very different protocols for the different children, and up to each child that allow us this. One of the first protocols that we have created was this hierarchical one, in which, so here you can see an example of what we were talking, with the NAO doing the exercise and pointing to the therapist, she will do it. And then it's the turn of the child to do it. This hierarchical protocol was different from before because it had hierarchy, so it had like very different levels, in which what we trained specifically were gestures. So we train like communicative gestures like hello, yes, short, that these children not many times have this kind of gestures. And then, okay, everything is appearing. Especially thing of this kind of protocols that we try to introduce was to not use the Wizards of Oz, but go to a more hybrid control, in which the NAO has some parts that are automatic, other parts are the therapists that control them, so that they are completely independent and they don't need an engineer in the room. This study was implemented both in Italy but also in Portugal. So these were the institutions in Italy, my university here in Italy, Fondazione Don Carlo Gnocchi, and the two institutions that we had in Lisbon that were specifically for autism. And we have done different kinds of study with a lot of therapists involved, children involved, and a lot of minutes of video that were important for us to explore our algorithms after. From this hierarchical protocol, we have created two other protocols that I am going to talk just because then the demo will focus on one of them, that is the sensorial and the bingo protocol, that try to be more overall, let's say, not as a lot of levels, but had a more holistic approach, and introduce this kind of songs that you can see here. Here the songs are in Italian, but I can show you that are basically they integrate the gestures inside a child's song, and this was important for the therapist because it allowed a better connection with the children. I'm going to take this and start it. Hope you can hear it. So this is a song, and at the same time you have the gestures like eating. So in this case it's crying. And here no one knows. Here is drinking tea, actually. And that's it. So it's this kind of songs. This is another example with an English song at least. But yeah, the gestures are always very simple so that the children can do it. And yes, so basically these are the kind of protocols that we have done so far, and the implementation of it has been done in two different modes, let's say. One in choreograph, that is like the starting point, because it's a multi-platform desktop application that allows us like to test the movements, and it's easier to implement more difficult gestures and also allows to monitor, to control, and to have very complex behaviors. Then what we do most of the times is to pass it to Python, because it has a higher execution time, so we can see directly what is happening with the robot, and it's much faster. So yeah, those are the two methods. Now I would go through choreograph just to show you some of the examples, because I don't have the robot here. So if you want to download it in case you had curiosity in the future, I left here the link of it, and basically this is a very simple software. Before it was crashing in my computer, so I hope now it's going to work. But yeah, here you have like the several box libraries with the several kind of movements that we can introduce in choreograph. And at the same time, we have the robot. So the simulated robot, in this case, I have chosen the last version of NAO. And basically you can see what would happen in a real robot. To connect, I will connect and hope everything will be fine. Exactly. And here this works a lot like by blocks. I don't know if you have already used it. It's very good because it's very simple, and sometimes to use it in the robot, it's the best. So, for example, to go to some posture, for example, to the sit-down posture, we can just go here and connect and do play, and the robot will sit. Okay, this is a kind of thing that we observe in this kind of simulators. Okay, and so here you can see the ground that is a bit balancing. The gravity here is a bit strange. But yeah, and then it works by programmation of blocks. So we just have to add the blocks that we want. So for example, for a stand-up block, so we can just stand up and then do other things. They have like here a mood section that I especially like, especially because working with children, we have like to have these different kind of moods. And for example, the happy one. They have here like the possibility to like change some of the parameters, or even to I don't know if this is what I wanted, or even to exactly show the code that is behind it. So it's possible also to do the code here, although I don't use it so much, but it's also a possibility. And then we just have like to connect the two and see what happened. Like I think first it will stand up and then you will be happy, I hope. Yes, this is more or less the times are very similar to what happened, and here the gesture of happy. And yes, so these are the kind of way that it can be used, the choreograph platform. And another thing, I use it particular for the movements, like for defining the gestures that I want. I can come here and basically see what are the degrees that I should use. So it's very useful in this case, because yeah, in other cases it would be very difficult to do it. And when it's connected also to the robot, I can see directly, like moving the robot, I can see directly what is happening here. And this is very, very useful, let's say. Another way to program this is through Python, as we have said before. So we have some simple example here, and basically this is all programmed in I don't know how to define this, but like a package that is called NAOkey. This was done by the NAO company. This has been programmed all in Python 2. That is a big disadvantage because it was never passed to Python 3. Although there is some connections with ROS, let's say, and it's possible to do the connection between NAO and ROS. In my case, we have used most of the time just Python because of the easy implementation, and it works that okay, we implement what package do we want from the several structures, and then we say okay, go to this posture, just sit down and do it. And so in order to do that, let's see, I have to use Anaconda to do it. And basically what I have obtained, okay, it's so if I do this, that is my simple example, and I show you here if everything goes nice and smooth, the robot just sits, okay? So, and we can observe what is happening at the same time that the code is running, okay? So this is the simplest thing, or if we wanted to stand up at the speed fraction, for example, faster, no, I just save, and if I have it here, I can put it to stand, exactly. So I do it very, very fast, or it tries to do it fast, but then it's hard, okay? So this is a very simple example of what we use. The specific code that is behind my work are several of these functions, but so I will focus on these two. That is one for the part of the NAO robot, and the other that is for the part of the camera. That for us is very important because of the measures that we can take, and also because of the mirroring part. Okay, the mirroring part, we need obviously a camera. So in this case, we no longer use the first version of Kinect, but we use Azure. That is the new one. And yes, so we have these two codes divided because the Azure runs in Python 3, and the NAO is still running in Python 2. And yeah, basically those are the two connections. And here you can see some of a simple example of what we are doing. So if I go here and it's like this, main pi, and then this one. Of course, for the therapists, we don't have this kind of code. We just have one exec that they click, and that's opening what you are going to see now. That is the main interface that they can use. And also, it always appears the camera so that they know what's happening, and in case we have any problems, they can report what is happening. So here this is the general one to put like the name of the patient and the name of the therapist, and the number of the session that they are doing. We also have female and the gender, just to have some statistics in the end, and also the principal hand used. This is especially important for the part of the mirroring. That's why we have this to say that is left or right hand. And yes, this is the last protocol that I have described you, that has the different kind of stimuli, with the luminous part, a sound part, and the movement part, and in which we can control. I don't want to increase it. We can control at the same time the robot. So here we can see, let me see with the choreograph open, and with this open, and for example, starting from the dancing part, so choreograph cannot reproduce the song. It can always reproduce the gestures, and basically you have like the dance part, and it shows what is really happening at the same time. So this is the choreograph as this thing that is very useful when one doesn't have the robot, that is to see everything, the simulation, and it is exactly like the robot. The only thing is the part of the sound, and also the part of the lights. Okay, it's not able to do it, the lights of the robot. Then we have other kind of things like the gestures that we have talked before. For example, the hello gesture, he says hello, or the angry gesture. This is very cultural and depends a bit. Let's see if it does. Okay, this is kind of hangry, like with the person, or the no gesture. This is more universal. So all of these are shown by the robot, and the therapists use this like to show the child the different kinds of gestures so that she can or he can reproduce. A thing that remains from the beginning, from the basic protocol that we had, was, I have like to stop it here. Exactly. And now I have to go to the mirroring part. This remains from the beginning, and to do the pure mirroring, in which you can see here. So here you can see my skeleton, now the key points that the Kinect is able to take out. These are basically the 3D positions of my body. I'm sure you have already talked about this in these workshops. And so here are my legs because you cannot see. So, and so if I do the pure mirroring, see if it works. And yeah, it's working. So here you can see that if I go with my hand or go with the other, or just do like this, so it's just mirroring the upper part, okay? In any case, this is very used by the therapists. They consider quite useful to do it with the children because they can play a lot and say that they are in an airplane, for example, or if they are dancing with the robot, or so there are a lot of different things that in this scenario can be reproduced. And yeah, this concludes basically the demo of my work. And now I would pass to the final part of the presentation that is not as fun because it doesn't have this kind of gestures, but it's a very important part, and the results are quite interesting. So I will just close all of these. So in the end, it asks to the therapist if she wants to save or not what they have done. And this will probably save, okay, and closes everything. And so coming back, after introducing this kind of measurements, what we have done was to develop some automatic measures based on the computer vision algorithms. That is the main work that we have developed. And basically, we have focused on 3 parts: on the action, the attention, and in the pose part. And related to the action part, we have created these 2 measures, one related to mirroring, because as you see, mirroring is very important in our work, and another related with the gesture recognition, that is the one that I'm going to focus. So we wanted to construct this gesture recognition because it was important for this kind of therapy, as you can see. What were the difficulties? And I wanted to have these videos to give you really the idea of how these sessions are done, is that we have children that are very small and that they go several times to the ground. So several times we don't see them. We cannot know in which moment they decide to do the gesture or not. That's why we have divided this into parts, in a part of action detection and another part of recognition. Most of the work has been in the action detection part because it was the most difficult thing that we have noticed and very important to the recognition. And what we decided to do was to introduce a kinetic parameter method that was able to define the beginning and the end of the movement. This departs from the idea that, okay, when we do a gesture, the person will have a moment with higher kinetic energy, and then it will go back to a state of no kinetic energy. Then we had the part of attention. It was one of the other algorithms that we have worked significantly. I will focus on this attention biomarker because it was kind of the main work of my PhD. The objective was to construct some kind of attention system classifier to understand where the child was looking at each moment. So if it was looking to the robot, if it was looking to the therapist, etc. And why was this difficult? Again, because of the positions that these children have. And also because we have this very frontal camera, we have just one camera. And basically the children are in have these cones in which we can situate, okay, say, okay, there the children is going to look to the therapist or to the robot, but as you see, are very, very thin cones. And this is an example, just to show you the different examples. And sometimes most of this was developed during the COVID situation. So we had like the improved thing of having a lot of masks. And this was also hard to just localize and to see where the highs were. What we decided to do was to use some algorithm that was the gaze 360 algorithm that already gave us like the gaze of each person at each moment, and join it with some definition of the areas of interest that were these kind of codes. So we have decided to define these codes. And with this, we classify if they were looking to the now and the other person. We have used like two methods for this definition. And just to say that one was more geometrical, one that was this, in which we define exactly the cone, and another that was a learning approach. So based on a lot of labeling that we have done, we had a model that learned what was the best with for each child and for each person. And what was the main problem here? This is a lot dependent on the position of the children and of the people, and a lot of times we have like good detections, but also very bad detections in which we don't have any kind of skeletons, as you can see here. So this generated some problems that we have corrected with another algorithm that I'm going to talk next. So these are the labeling part. It was a lot of hours of labeling, and this was particularly interesting because of it. What we had was these two approaches, and in the end, the learning approach was better, and the system was able to generalize. And these were the kind of interesting graphs that we have obtained both for the therapists and for the children. So here what we have is the representation of the gaze, so where they are looking. And what we could see was that the therapist, while the therapist was very focused on the subject, also at some points towards the now and towards the computer, the children tend to focus a lot on the now, on the robot, and on the computer, and not so much on the therapist. This was interesting to verify because this was already described in the literature, and it was good that our algorithm was really reflecting it. So that was very important for us. Another thing was that we were able to create this measure that we call the total fixation duration. That was how much time they were looking for each person, each part of the therapy. And this was important for the therapists because we gave these graphs to the therapists, and they could tell, okay, yeah, this really reflects what is happening during the sessions. And it was good to have this interpretable AI tool. After we have focused on the loss of the skeletons that we have obtained. So as you can see, we had very different positions and of the children. And many times, I didn't talk about this, but many times we had children that were in the legs of the therapy, so they were hugged by the therapist. This is very common in this kind of therapies. So we lose even more the possibility to see their skeleton, and it becomes even harder. So we wanted to construct this 3D reconstruction model. To do that, what we have used was picking a method that is already in the literature, but of course, these methods have the big thing of being done for adults, basically. They are not done for children. So what happened in this reconstruction method was that when we saw the child was represented very far away, and as an adult, not as a child. So what we decided to do was to do an adaptation of a parameter of the model that was this focal length that reflected the height of each person. And to do that, we just have done a simple linear model of this focal length estimation, and tried to test it in two different scenarios. One more constrained to understand how it compared with other methods that are the baseline for 3D reconstruction of the points of the skeletons of the person, and another in the real therapies. In real therapies, of course, we don't have the amount of cameras necessary to do this kind of very precise tests. So our comparison was mostly done in terms of this dice similarity, in which we basically compared if the figures were related or not. Basically, our reconstructed figure was related with the baseline that we had or not. And what we obtained was, in our case, was quite good. We were equal to the state of the art most of the times, equal and above the state of the art, which was very good, and very close to some of the skeletons of the Kinect that we could extract, that were very few. As you can see here. So what happened here is that we have the several pairs of therapist and child, and we can really see what was the problem is that we lose a lot of skeletons. So a lot of those skeletons that we have seen, we didn't have. And with our method, we were able to recover most of them. And so overall, the achievements here are these three systems that I've described, with the gesture recognition and attention manager and the 3D pose estimation for children. Then we decided to look specifically on some experimental studies that we have done. We have done two big studies, and here I just report one of them, that is the CADIN one, because of the time that now is finishing. And basically this study was done between May and June of 2022. This was a bit better because we didn't have like the masks. And it was the training of that hierarchical protocol that I sent before during 9 weeks. And what we had as main measures, let's say, so what we measure in the beginning and the end of the study was this clinical scale. So we try to compare a clinical scale with some measure that we have produced, that was this total fixation duration measure. And we have done this in for 22 children. So the children that arrived in the end were not the same number, because of course there are family problems sometimes that make some problems in terms of logistics. Some of the children don't deliver the clinical scale, and with that we cannot do anything like a comparison with our algorithm. But overall, what we verified and was good was that the clinical scale in the experimental group, so in the group that have done with the robot, improved. So that was very nice. And on the other way, the total fixation duration towards elsewhere. So that measure that we have defined for the robot, we have defined for the therapist, and we have defined for all the part that is surrounding them. And what we verified was that in the case of the experimental group, the one that has done with the robot, this measure decreased. And this was kind of interesting. More interesting was the fact that we had a connection between these two measures. So a connection between a measure that we have produced from the algorithm that we have done that was automatic, and the clinical measure that is a measure that the doctors use. And what we noticed was that looking less to elsewhere during the therapy led to a larger improvement in the outcome measure. What we expect, because if the child is more focused on the interaction with the therapist and with the robot, we expect that the clinical measure that reflects their communication abilities improves. And with that, I go to the conclusion. So basically, this work has evaluated the clinical INSPIRE protocol. I think I've shown you how we implement this in real models, like say in Choreograph and in Python. We have defined this automatic measure, and we conducted 2 experimental studies and showed changes in outcome measures. The contributions are several, with several institutions and children involved. And in terms of future work, some of the future work is related to heterogeneity. So we want to develop more personalized robotic systems. Another problem is connected with the familiar organizational problems that we have seen before as a big problem. So we want to increase the parents' involvement, either by parents guided sessions, so interaction during initial sessions, or an extension. This is our final goal. The final goal of the project is an extension to our home settings using this kind of robotic simulators that I have shown you as a first step to introduce it in a home scenario that is much more hard than a clinical scenario. So I finish my presentation thanking to my students that have helped me a lot on this work. And I thank you all for your attention, and I'm open for questions, although I know that I've exceeded a bit my time. Thank you.
Thank you very much, Laura, for such a fascinating topic and your presentation. Yeah. So we have some questions here. Yeah, please come forward. Yeah, maybe you can sit here. Just a moment. Yes. Thanks. Yeah.
So, Professor Laura, I have just one question.
Yes.
What is the role of the NAO robot in the therapist and child's dynamic? As in, whenever a therapist is conducting a particular session with the child, does the robot play an indirect role, or is it like a human in the loop kind of system, where the therapist will just pick one of the particular programs, pre-programs that the NAO robot is designed to have inbuilt in its system, then shows it whenever the NAO is demonstrating it, and then the child picks it up from the therapist, or is it the other way around?
So I didn't that you are right. I should have explained this better, but the NAO has a role of mediator. Okay, so is there permitting the interaction between the therapist and the child. Okay, the NAO has pre-programmed, some pre-programmed algorithms, okay, that run directly, and that the therapist can actionate. So it can say, okay, go. And as I've shown you in the interface, so some of these things are the therapists that decide in a certain moment to use them. Okay, and this is important because it's not, so we have this protocol defined, okay, this big protocol, but then it's the therapist at each moment evaluating the reaction of the child that she is having at each moment that decides, okay, it's better to do this exercise or it's better to do that exercise. Okay, so it's a connection between the two. The thing why we use the robots is just because, as you've seen from the graphs of the attention, is the children have a lot of attention towards the robots and tend to be more focused. So these children disperse all the time in the therapies, and with the robot they have like a focus of the attention, and this allows the therapists to do better their work. But the objective is not to substitute the therapist. Okay, the objective
Yeah,
is like to really work with the therapist.
yeah, yeah. But okay, while we're on that topic, I would also want something else popped in my mind, in the back of my mind. See, the general perception about robotics is that robots cannot feel, process, or display emotions. Although that is changing bit by bit, day by day, the general notion of robotics being able to process emotions is still far from reality. How would your research be able to overcome this particular stigma?
The stigma with the emotions. So I think that in part, the robots are. So of course, it's true that the robots don't show a lot of emotions, but they can show some. Okay, even with let's say with the LEDs and with the gestures and with the what they say, they can show something. Okay, so we play a lot around these three different issues to to try to show something with the robot, but also we don't want like to overload the child. So we have to be very attentive. That's why we have that big interface with a lot of options for the therapists, because each child has different sensory abilities. So some children may like that the robots show these kind of emotions, but some children don't like at all. So they prefer not to have it, or just have like the sound, or just have a small movement. So we play with this to go more towards this direction. But this field in particular, the robots showing emotions, are let's say is very gradual, that can happen. The best would be to be in an automatic way. That is our, like, one of the fields that our research is going, is like to understand how the child is feeling, so that the robot can suggest what is better for her. Okay, in terms of the lights, of the sounds, etc. Hope I
Yeah.
have answered your question.
So it's basically, let's just say robots do stuff, but it's like robots try their best to understand and process the emotions and then give the almost, what to say, predicted response to the kid. In a way, it would comfort or
Yeah,
reassure human, right?
yes, that is a bit the objective. Is like to show the emotions based on what the child is doing. So now this is controlled by the therapist. Ideally, it will be more automatic. Okay, these are the main directions.
Okay, thank you.
Thank you.
Good morning, ma'am. This is Jaykant here
Good
from
morning.
SRM. Actually, I'm just, you're using the choreograph to do the controls of the NAO. And you still have more applications that you are doing it separately, right, ma'am? So
Yes.
how you interface with the external applications? Because you're giving with for the demo that you're giving some constraints and you click on that one and it performs the task separately, right? So what way
Yes.
you interface with that modules?
So basically, so I have the choreograph is one thing that I use more for, let's say, a training part. So it's more like when I'm in the beginning of creating these clinical protocols, no, really
Okay.
in the beginning, and I use those blocks like just to see, okay, the robot does this, does that. I move the robot and I have these angles, okay. But after having these angles and these things defined, what I do is to transfer these angles that are defined directly to the to the Python. Okay, I can show you, like, this is a lot of code, but just to give an example precisely. So I use the angles that I collected from there and put them here. Okay, put them here,
Okay.
like to say to the robot, okay, this is what you are going to do. So it's a platform that I use. It's basically for my training, no, for
Okay.
knowing what I should
Uh,
put here. But the rest I do it all in Python because it allows me a better connection with all the external APIs. So with all the sensors, the part of the algorithms of the gesture recognition algorithm, I need to have a neural network running. So if I need to have this network running, I need to be in Python and program in Python. So I really just use choreograph as a baseline. But there are people, for example, there are therapists that use it really to program and have small programs in the robot to use it with children. But not our case in our like more developed clinical protocols.
it's kind of API that you are building it.
What? Sorry, I didn't
Uh,
understand.
this kind of APIs that you integrated.
I integrated so I integrate different kind of programs of APIs.
Okay.
So they are the API of Azure. Let's say this is one of the ones that I use related to the camera. Then I have this API, for example, of the NAO that has all this kind of language of itself. And then I have the APIs related with the neural networks. Now that I use basically PyTorch and TensorFlow, more PyTorch now to really have the full like to construct my networks.
Thank you, ma'am.
Thank you.
Thank you. Yeah. I just had a small question about how, I mean, you see you're using PyTorch or TensorFlow, right? So in real time, like, where is the processing happening? Like, is it offloaded to a separate server or?
No, it's this is one of the things here. Um, so we have always privacy issues. Okay, so we cannot run in servers. Okay, so we have all running is locally. Okay, we have even the gesture recognition part is running locally. We train in some servers that we have, but from the lab, like from this lab, for example, or also in Polyme, we have like a big server in which we can train. But even in those cases, they have to be inside the institution because of privacy issues. This is a thing that we have to respect because they are children. Okay, this I didn't underline this topic a lot in my presentation, but it's really important, and it's something that we had and also created constraints in our algorithms and in our protocols.
Okay. Oh, thank you. Thank you for your that's all.
Thank you.
Thank you very much. Okay, thank you very much for the wonderful session, Laura, once again. And a very short question from my end. I was curious to know that you are showing this marker-based attention model, something, right? So the
Yes,
marker attention-based classification model. So it is showing where the children is looking on to the to the robot or the therapist, correct? So
yes.
that is also over the sessions.
Yes, that also happened actually over the sessions. What we verify, I can.
Yeah. So I
Sorry,
was wondering.
I was just now over the sessions. What we verified actually,
Yeah,
that
because I
was
was
one of
wondering
the
whether.
things that we
Yeah.
want to improve is that they look to the now a lot in the beginning, so they
Yeah.
are very interested in the now, but then they have like a collapse of
Interest
attention,
towards.
and
Yeah,
I
that is
think
what I
this
think.
is yes, yes, that was interesting. Like most, even if it's above, like you can see that in several cases it's above of what is they are looking to the therapist. But these results were very important for us to justify the fact that we need more personalized protocols. No, because in the beginning they have like that first. The first moment of looking to the robot and these new protocols and everything, but then they lose attention because they are already used to the protocol. So they have already these, they know what is going to happen. And that is good for one side, but at the same time, they become a bit bored. So we have like to create, to adapt better our robot to the different children. That's what we think after looking to these results and also looking to them with the therapist. Let's say after analyzing them, that was our main conclusion.
Okay, so this kind of research, are you using it for any personalized treatment plan to understand the prognosis?
This is what we are trying to use it actually right now.
Yeah,
Right now we are
because that's
actually
really
seeing.
interesting to do so, right? Because since you
Yes,
have different
we are.
factors for different children.
Yes, yes, that is one of the things that we want to do right now. And we are having a master thesis exactly on that, on personalization. And basically, what we are using is not just this, like not just this marker of the attention, but also the marker related with the gestures that they are doing or not, and the marker related with the position they have in the room. Because we have also noticed that in the beginning, like with the sessions, they tend to be more concentrated around now, and they tend to like not disperse so much in the room. So we are using these different metrics to create a reinforcement learning strategy to personalize more the our protocols and to try to like use the information that we have from the therapist. So we recall every time the levels that the therapists are doing and try to understand based on the levels that the therapists are doing, based on the attention that the robot has, the robot, no, the child has towards the robot and towards the therapist, try to understand better what should be the next level, like the next exercise that we should propose with the robot.
Okay, thank you very much, Laura, once again.